Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to this explainer. All right, let's jump right into this. Imagine, just for a second, leaving the cozy, familiar, three-dimensional world we live in. You know, the world where you can point up, down, left, right, forward, and backward. Well, we are about to embark on a journey into a totally mind-bending, abstract realm, the world of infinite dimensional spaces. This is the universe of functional analysis. It's an incredible mathematical framework that perfectly synthesizes linear algebra, real analysis, and topology, giving us the tools to rigorously study spaces where dimensions quite literally never end.
So, I want you to pose this central question to yourself: what actually happens to geometry when dimensions just never end? See, in finite spaces, algebraic dimensions dictate pretty much everything. But as we stretch out into infinity, the standard rules of distance, length, and structure completely break down. They have to be meticulously rebuilt from the ground up using subtle topological phenomena and really rigorous algebra. Today, we're going to explore exactly how mathematicians survive and navigate in this infinite landscape.
Here is our roadmap for today. We'll start with the infinite dimensional framework, then cross the finite versus infinite divide. Next up, core principles and operators, followed by duality and weak convergence, spectral theory of operators, and finally, we'll wrap up with the geometry of Hilbert spaces. Let's get to it.
Section 1. The Infinite Dimensional Framework. Building the Rules of the Road. Okay, so before we can run in infinite dimensions, we kind of need to know how to take a single step, right? We have to establish the rules for measuring distance using norms and metrics. And that brings us to a massively fundamental concept, the Banach space. Think of a Banach space like a vector space paired with a geometric measuring stick, which we call a norm. But the absolutely crucial part here is that it has to be complete. Completeness acts as our mathematical safety net. It essentially means that every Cauchy sequence, a sequence where the terms get closer and closer together, is totally guaranteed to converge to an element that actually exists within that space. If you have an absolutely summable series, completeness guarantees it will converge to a real vector right there in your space. Basically, nothing falls through the cracks.
Now, don't worry, you don't need to memorize all these rigorous equations, but just take a look at the sheer variety of these abstract spaces. We've got sequence spaces like the LP spaces, spaces for bounded sequences, and even spaces made entirely out of continuous functions over an interval. Each of these different environments has its very own specific norm, its own unique way of measuring distance, but they all share that essential completeness structure we just talked about. They are all complete Banach spaces, acting as completely reliable stages for complex mathematical operations.
Section 2. The finite versus infinite divide. The weirdness of infinity.
All right, we are now officially leaving the safety of finite dimensions. Let's quickly contrast these two worlds. In finite dimensional spaces, like a standard 3D grid, all norms are equivalent. Honestly, it doesn't matter how you measure distance, the underlying shape and topology of the space remain perfectly isomorphic. But in infinite dimensional spaces, that structural harmony totally collapses. If you simply change how you measure distance, if you change your norm, you can induce an entirely different topology on the exact same vector space. The space literally morphs depending on your measuring stick. It's wild. So the crucial point here is understanding just how vast this infinite space really is. And there's a mathematical tool that brilliantly illustrates that vastness, Rice's lemma. In simple terms, Rice's lemma proves that if you have a closed, proper subspace, you can always step outside of it. You can always find a unit vector, a vector of length 1, that stays a specific distance away from that entire subspace. You literally never run out of room to step away into a new orthogonal-like direction.
And because you never run out of room, we encounter this shocking geometric phenomenon. In infinite dimensional spaces, the closed unit ball is never compact. In our standard finite geometry, the classic Heine-Borel theorem tells us that if a shape is closed and bounded, like say a solid sphere, it is compact. But Rice's lemma allows us to construct an infinite sequence of vectors inside that bounded sphere, all spaced a fixed distance apart from one another, with absolutely no convergent subsequence. So you have a bounded, closed shape that isn't compact. It completely defies our everyday geometric intuition.
Section 3, Core Principles and Operators, Tools of Survival. Because our everyday intuition is so broken in infinite space, we're going to need some new tools to survive. Here are the 4 structural pillars of functional analysis. We have the uniform boundedness principle, the open mapping theorem, and the closed graph theorem. And crucially, we have the Hahn-Banach extension theorems. Hahn-Banach is absolutely vital because it guarantees that we can construct dual spaces. It ensures we always have non-trivial bounded linear functionals, which basically means we always have a way to measure and separate these abstract infinite dimensional objects, no matter how weird the space gets.
Now, while classical textbooks often prove those principles separately using pretty complicated category theorems, let's look at this beautiful unification instead. Zebriko's lemma. It establishes that a countably subadditive seminorm on a Banach space is automatically continuous. Now, what does this matter? Well, because Zebriko's lemma elegantly unifies the uniform boundedness principle, the open mapping theorem, and the closed graph theorem under one single powerful theoretical framework. It's like a master key that just unlocks all the core principles at once.
Section 4, Duality and Weak Convergence, Redefining Limits.
So now that we've built the space and found our tools, how on earth do we track movement when standard distance fails us? Well, we have to completely redefine limits. In infinite spaces, demanding that the actual distance between a sequence and its limit shrinks to absolute zero, what we call strong convergence, is often way too restrictive. So mathematicians use weak convergence. Instead of measuring direct distance, weak convergence evaluates movement indirectly through continuous linear functionals. It's almost like watching the shadows of the sequence rather than the sequence itself. In infinite space, sequences can easily converge weakly without ever converging strongly. It's just a broader, much more forgiving way to track limits.
Section 5, Spectral Theory of Operators. Finding the DNA.
Now we are transitioning to the real climax of the theory. In finite matrices, you basically just have eigenvalues, right? But look at what happens in infinity. The spectrum, which is kind of like the operator's DNA, splinters into a disjoint decomposition of 3 distinct parts. First, you have the point spectrum, which are your classic eigenvalues. Second, the continuous spectrum, where the range is dense but the inverse is unbounded. And third, the residual spectrum, where the range isn't even dense. So a simple eigenvalue in our 3D world literally shatters into complex, incredibly rich behaviors when stretched into infinite dimensions.
Section 6, Geometry of Hilbert Spaces. The return to the familiar. Phew! After all this weirdness, we are finally landing safely in Hilbert spaces. These are complete, inner product spaces which magically restore comforting concepts to us, like angles and orthogonal geometry. Notice the different operator classes we encounter here: normal, unitary, positive, and self-adjoint operators. And here's a massive takeaway for you. A self-adjoint operator, where the operator equals its own adjoint, always has real eigenvalues. And this isn't just abstract math. In quantum mechanics, these self-adjoint operators represent actual, measurable physical observables. How cool is that?
All of this builds into the absolute crown jewel of the subject, the spectral theorem. This theorem beautifully dictates that compact self-adjoint operators can be perfectly diagonalized. The proof itself is this elegant 4-step dance. Step 1, we establish norm attainment at an extremal eigenvalue. Step 2, we use induction via orthogonal reduction, peeling away invariant subspaces. Step 3, we verify termination or sequence convergence to 0. And finally, step 4, we achieve the final representation, a perfect direct sum decomposition of the space.
And that leads us to our final, pretty profound question. How do these abstract, infinite dimensional frameworks
frameworks built purely in the minds of mathematicians to deal with the weirdness of infinity, so perfectly modeled the physical universe in quantum mechanics. The shocking truth is that the bizarre, totally unintuitive math of functional analysis, complete with its weak limits and infinite spectra, turns out to be the exact native language of quantum reality. It really leaves you wondering, did we invent this math, or did we just discover the source code of the universe? Thanks for joining me on this explainer, and I really hope this sparks your curiosity to keep exploring.
Like what you share.
This website makes learning so easy. I found all my resources here.
Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious mind.